Hello, and welcome to the Sleepy Astronomer. Tonight, you're traveling through space at 828,000 kilometers per hour, riding a planet that orbits a star that orbits the center of a vast spiral of 400 billion suns. This is your cosmic address, your galactic home, and tonight, we're going to explore every beautiful detail of the Milky Way's gentle spiral dance. Whether you're tucked under blankets in a city where streetlights wash out the stars, or perhaps in a place where you can still glimpse that faint river of light arcing overhead, you're exactly where you need to be for tonight's cosmic drift. If you're new to these starlit wanderings, welcome. If you've journeyed with me before, thank you for returning. Tonight, we'll drift from your backyard, where you might glimpse that faint band of starlight on a clear night, all the way out to discover why our galaxy spins in such an elegant spiral. We'll meet our stellar neighbours, learn how the very atoms in your body were forged in the heart of this cosmic city, and follow the slow, patient dance that our solar system has been performing for billions of years as it orbits the galactic centre. We'll explore the gentle architecture of spiral arms, visit with our approaching galactic neighbour Andromeda, and consider what it means to be citizens of not just Earth, but of this vast, rotating island of stars. So, settle in, let your breathing slow, and prepare to see yourself as a traveller, moving through space at incredible speeds, riding our planet through the gentle arms of our cosmic home. Step outside on a clear night, away from the glow of streetlights and porch lamps, and let your eyes adjust to the darkness. It takes about 20 minutes for your pupils to fully open, for the light-sensitive cells in your retina to become their most receptive. But it's worth the wait, because slowly, gradually, something magnificent begins to emerge from what first appeared to be just scattered points of light. There, stretching from one horizon to the other like a faint river of starlight, is our galaxy, the Milky Way. Not some distant astronomical object, but our cosmic neighbourhood, our galactic home. That pale band of light contains everything we've ever known, every star we've ever seen with the naked eye, every planet in our solar system, and hundreds of billions of other worlds we can only imagine. The ancient Greeks called it the Milky Circle, Galaxias Kyklos. The Romans saw it as Via Lactea, the Milky Road. Aboriginal Australians spoke of it as the campfire smoke of their ancestors, drifting across the sky. In Finland, it was known as the Path of the Birds, while in parts of Africa, it was called the Backbone of the Night. Every culture that has ever looked up at a dark sky has seen this pale river and wondered what it might be. But here's something beautiful to consider as you stand there in the darkness. You're not simply observing the Milky Way from some external vantage point. You are the Milky Way. Every atom in your body, every breath you take, every thought drifting through your mind is made of material that was forged in the hearts of stars within this very galaxy. You're not a tourist visiting a cosmic destination. You're a citizen of this vast spiral city, looking at your own cosmic backyard from the inside. Think about that for a moment. The calcium in your bones was created in the dying moments of a massive star somewhere in our galactic neighbourhood. The iron in your blood was forged in a stellar furnace and scattered into space by an ancient supernova. The oxygen you're breathing right now was gifted to the galaxy by countless stars over billions of years. You are quite literally made of the Milky Way, and tonight you're using those stellar atoms to contemplate the very galaxy that created them. What you're seeing when you look at that faint band of light is our galaxy from the inside. Imagine living inside a vast, flat disk, scattered with hundreds of billions of glowing embers. From your position, roughly 2/3 of the way out from the center, when you look toward the edge of the disk, you see relatively few stars. But when you look toward the center, or along the plane of the disk, you're looking through the densest concentrations of stars in our galaxy. That's what creates that milky river of light, thousands upon thousands of distant suns blending together into a soft, continuous glow. Our cosmic address is quite specific, actually. We live in what astronomers call the Orion Arm, sometimes known as the Local Arm, a minor spiral arm about halfway between two major ones. Think of it as living in a cosmic suburb, not quite in the bustling downtown of the galactic center, nor in the sparse rural areas of the galactic edge, but in a comfortable neighborhood with tree-lined streets and friendly neighbors. But most of us have lost touch with this magnificent view. Light pollution from our cities and towns has washed out the Milky Way for roughly 80% of people on Earth. Many children today grow up without ever seeing our galaxy stretched across the night sky. They might glimpse a few dozen stars on a clear evening, but the great river of light that captivated ancient astronomers and inspired countless myths and stories remains hidden behind a veil of artificial illumination. This disconnection represents more than just an aesthetic loss. For thousands of years, humans navigated by the stars, planned their agriculture by celestial cycles, and found their place in the cosmos by understanding their relationship to the night sky. Polynesian navigators could cross thousands of miles of open ocean using only the stars as their guide, reading the sky like a detailed map. Desert nomads use star patterns to find their way across seemingly featureless landscapes. The Milky Way wasn't just beautiful, it was practical, serving as a cosmic compass pointing the way home. Even today, when you do manage to find a truly dark sky and see the Milky Way in all its glory, something profound happens. There's a moment of recognition, almost like meeting a family member you've heard about but never seen. Your perspective shifts. The universe suddenly feels less empty, less cold, less indifferent. You realize you're part of something vast and ancient and ongoing. You're not separate from the cosmos, you're embedded within it. The feeling is sometimes called the galactic perspective, similar to the overview effect that astronauts describe when they see Earth from space. But instead of seeing our planet as a fragile oasis in the cosmic desert, you see yourself as part of a magnificent stellar community. The loneliness that can sometimes accompany stargazing, that sense of being a tiny speck in an incomprehensibly large universe, transforms into something more like cosmic citizenship. You belong here. This is your home, just on a scale much grander than you might have imagined. Aboriginal Australians have maintained this connection more than perhaps any other culture. Their Dreamtime stories speak of the Milky Way as a river where the spirits of the ancestors travel, connecting the living world with the eternal. In their tradition, certain stars mark watering holes along this celestial river, and the dark patches between the bright star clouds aren't empty space, but rather the silhouettes of animals and spirits moving across the sky. They see not just a band of light, but a living, breathing story that connects their earthbound existence to the cosmic order. The ancient Maya also wove the Milky Way deeply into their cosmology, calling it the World Tree or sometimes the White Road. They saw it as the cosmic axis around which the universe revolved, and they aligned their most sacred temples and pyramids to track its movement across the night sky throughout the year. Their entire calendar system, with its intricate cycles within cycles, was designed to harmonize earthly life with these great galactic rhythms. Even as recently as a century ago, when light pollution was minimal, people had a much more intimate relationship with the night sky. Farmers could tell time by the position of constellations. Sailors used star patterns for navigation. Children learned to identify the brightest stars and could point out the summer and winter portions of the Milky Way. The galaxy wasn't an abstract scientific concept, but a visible, constant presence that connected daily life to cosmic time. Part of what makes the Milky Way so mesmerizing when you finally see it clearly is its delicate structure. It's not a uniform band of light, but rather a complex tapestry of bright regions and dark lanes. The bright patches are where we're looking toward dense star-forming regions, or the bulging center of our galaxy. The dark areas aren't empty, they're dust clouds silhouetted against the more distant stars, cosmic shadows that sculpt the light into intricate patterns. These dark nebulae have their own names and stories. The Great Rift, a dark lane that splits the Milky Way from the constellation Cygnus down toward Sagittarius, was seen by many cultures as a cosmic river or roadway. Some Native American tribes called it the Dark River and told stories of spirits canoeing along its length. In Australia, it's known as the Emu in the Sky, the dark silhouette of a great bird stretching its neck to drink from a celestial waterhole. When you're lying on your back on a clear moonless night, far from city lights, watching the Milky Way slowly rotate overhead, you begin to sense something that our ancestors knew instinctively. Time moves differently out there. Our galaxy operates on scales that dwarf human experience. The light you're seeing from the galactic center left its source roughly 26,000 years ago, when our ancestors were painting the first cave art and learning to shape stone tools. The stars that appear to be next to each other in that pale river might actually be separated by hundreds or thousands of light years. And yet, there's something deeply comforting about this cosmic perspective. The Milky Way has been there, essentially unchanged, for countless human generations. It witnessed the rise and fall of civilizations, the migration of peoples, the development of language and art and music. It was there when the first humans looked up and wondered what those lights might be. It will be there long after our current cities have crumbled and new ones have taken their place. This continuity offers a kind of peace that's hard to find in our fast-paced modern world. While everything around us seems to change with dizzying speed, the great spiral of our galaxy turns with majestic slowness, completing one rotation every 225 million years. From this perspective, human history is but the briefest moment, and yet every human who has ever lived has lived under this same starlit canopy, has been a citizen of this same cosmic city. So the next time you find yourself somewhere truly dark, somewhere that artificial lights can't reach, take a moment to step outside and look up. Let your eyes adjust to the darkness. Find that pale river of light stretching from horizon to horizon, and remember that you're not looking at something separate from yourself, but rather at your own cosmic home, the vast, stellar neighborhood where you've always belonged. You're seeing the galaxy that made you, and you're using atoms forged in its stellar furnaces to contemplate its beauty. You're looking at home from the inside, a perspective that's both humbling and profoundly connecting. And as we drift deeper into tonight's exploration, we'll journey outward from this intimate view, this personal connection to the night sky, to understand the grand architecture of our galactic home. We'll discover how this beautiful spiral came to be, why it spins the way it does, and what it means to be passengers on a small planet orbiting an ordinary star in one of the outer neighborhoods of this extraordinary cosmic city we call the Milky Way. If you were to write your cosmic address, it might look something like this: Earth, Solar System, Orion Arm; Milky Way Galaxy, Local Group; Virgo Supercluster, Observable Universe. It's quite a mailing address, isn't it? But tonight, let's focus on that middle part, our position within the Milky Way itself, because understanding where we live in this vast stellar city helps us appreciate just how remarkable our cosmic neighborhood truly is. Imagine you're floating high above our galaxy, far enough away that you could see its entire structure spread out below you like a vast pinwheel of stars. What you'd see is a relatively flat disk, perhaps 100,000 light-years across, but only about 1,000 light-years thick. Picture a dinner plate with a fried egg in the center, the yolk representing the bright central bulge where older, yellower stars cluster densely together, and the white representing the flatter disk where younger, bluer stars trace out graceful spiral patterns. From this cosmic vantage point, you'd notice that our galaxy isn't uniform. It has structure, architecture, personality. The spiral arms curve outward from the central region like the arms of a cosmic hurricane frozen in time, each one containing billions of stars, vast clouds of gas and dust, and the bright stellar nurseries where new suns are being born even now. Our solar system sits roughly 26,000 light-years from the galactic center, about halfway out to the edge. If the Milky Way were the size of a large city, we'd be living in a pleasant suburban neighborhood. Not quite downtown, but certainly not in the rural outskirts either. This location turns out to be rather fortunate for life as we know it. Too close to the center, and we'd be bathed in harmful radiation from the supermassive black hole that lurks there, not to mention the frequent stellar explosions and intense gravitational disturbances. Too far out toward the edge, and there wouldn't be enough heavy elements, the carbon and oxygen and iron that make rocky planets and living beings possible. Astronomers call this sweet spot the galactic habitable zone, and we happen to live right in the middle of it. It's a bit like the Goldilocks story, but on a galactic scale. Not too hot, not too cold, not too chaotic, not too sparse, but just right for planets to form and evolve complex chemistry over billions of years. Our specific neighborhood has a name, the Orion Arm, sometimes called the Orion Spur or the Local Arm. It's what astronomers classify as a minor spiral arm, a smaller branch that connects two of the galaxy's major spiral structures. Think of it as a side street that connects two main boulevards, the Perseus Arm farther out and the Sagittarius Arm closer to the galactic center. The Perseus Arm, our outer neighbor, is named after the constellation Perseus, which lies in that direction from our perspective. It's a major spiral arm rich in young, hot blue stars and active star-forming regions. If you could see it from above, it would appear as a bright, well-defined curve of stellar light sweeping around the galaxy's outer regions. The Sagittarius Arm, our inner neighbor, is visible to us when we look toward the constellation Sagittarius during summer evenings. This is why the summer Milky Way appears so much brighter and more dramatic than its winter counterpart. We're looking inward through our local arm toward this major spiral structure, dense with stars and glowing nebulae, toward the heart of our galactic home. But spiral arms aren't fixed structures like the spokes of a wheel. They're more like traffic jams on a cosmic highway, regions where stars and gas clouds pile up temporarily as they orbit the galactic center at different speeds. The arms themselves rotate, but more slowly than the stars within them. Individual stars drift into an arm, spend some time there adding to its brightness, then continue on their orbital paths, and eventually drift out the other side. It's a bit like being in a slow-moving traffic jam on a circular highway. Cars enter the jam from behind, creep through the congested area, then accelerate out the front and continue their journey around the track. The jam itself moves around the highway, but much more slowly than any individual car. In our galaxy's case, this process takes about 100 million years for a complete cycle. This means that throughout the history of life on Earth, our solar system has drifted in and out of spiral arms multiple times. When we're in an arm, the night sky would have been more crowded with bright stars and active stellar nurseries. When we're between arms, as we are now, the sky is somewhat quieter, with fewer massive stars nearby to disrupt planetary systems with their intense radiation and eventual explosive deaths. Some scientists have speculated that these passages through spiral arms might have influenced the evolution of life on Earth. During arm crossings, increased cosmic ray exposure and nearby supernovae could have triggered ice ages or extinction events. Conversely, the gravitational disturbances might have shaken comets loose from the outer solar system, increasing the rate of impacts on Earth. It's a fascinating possibility that connects our planet's biological history to the grand architecture of our galaxy. The ancient Mesopotamians, skilled astronomers despite their lack of telescopes, noticed that certain stars seemed to cluster along what they called the path of Anu, their sky god. They were observing, without knowing it, the projection of our local spiral arm against the celestial sphere. Different cultures have interpreted this stellar roadway in various ways. Hindu astronomy speaks of the bright path along which the souls of the departed travel to reach the realm of the gods. In Norse mythology, it was the bridge Bifrost, connecting the world of humans to the realm of the gods. Modern astronomy has revealed that our local arm contains some of the most familiar sights in our sky. The bright stars of Orion, for which the arm is named, are part of a vast star-forming complex within our cosmic neighbourhood. The Pleiades star cluster, that delicate gathering of blue-white stars that has inspired poetry and myth in cultures around the world, is also a local resident. Even the North Star, Polaris, which has served as a celestial lighthouse for countless generations of navigators, shines from within our local galactic suburb. What's remarkable is that we can actually see the structure of our local arm from the inside. Those summer evenings when the Milky Way stretches across the sky in all its glory, we're looking along the plane of our spiral arm, through layers upon layers of stars and star-forming regions. The Great Rift, that dark lane that seems to split the Milky Way in two, is actually a series of dust clouds within our local arm, silhouetted against the more distant stellar light. From our perspective embedded within this structure, mapping the exact shape and extent of the Orion arm has been one of astronomy's great challenges. It's a bit like trying to map the layout of a city while standing in the middle of a crowded street. You can see the buildings immediately around you, and you might glimpse some distant landmarks, but getting a clear picture of the overall urban plan requires careful observation and clever detective work. Radio telescopes have been particularly helpful in this cosmic cartography. By detecting the radio waves emitted by hydrogen gas throughout the galaxy, astronomers can trace the distribution of material in spiral arms even when dust blocks our optical view. These observations have revealed that the Orion arm is about 10,000 light-years long and roughly 3,500 light-years wide, a substantial structure but still just a minor feature compared to the galaxy's major spiral arms. What makes our local arm special isn't just its size or structure, but its history. This is where our solar system formed 4.6 billion years ago, condensing from a cloud of gas and dust enriched with heavy elements from previous generations of stars. The calcium in our bones, the iron in our blood, the oxygen we breathe, all were forged in stellar furnaces elsewhere in this arm and scattered into space by ancient supernovae and stellar winds. In a sense, the Orion Arm is our ancestral home, not just the place where we happen to live now, but the stellar nursery where our entire solar system was born. The same vast cloud that gave birth to our sun also produced many of the stars we see in our local neighborhood. We're not just residents of this cosmic suburb, we're part of a stellar family. Siblings in the truest sense, all born from the same galactic materials in the same general region of space. This perspective transforms our relationship with the night sky. Those stars twinkling overhead aren't distant, foreign objects, but rather our cosmic relatives, fellow travelers, sharing the same general path through the galaxy. When you look up at the constellation Orion on a winter evening, you're seeing some of our nearest galactic neighbors, brilliant blue giants that formed from the same enriched gas and dust that gave birth to our own solar system, though at a much later time. The ancient Chinese astronomers organized their sky into 28 lunar mansions, cosmic neighborhoods that the moon would visit during its monthly journey. They understood, in their own way, that the heavens had structure and organization, that stars weren't randomly scattered, but formed meaningful patterns and relationships. They were mapping, without modern instruments, the local architecture of our galactic home. Our cosmic address continues to evolve. The solar system orbits the galactic center at about 220 kilometers per second, fast enough to circle the entire galaxy in roughly 225 million years, a period astronomers call a galactic year. During Earth's history, we've completed about 20 of these great orbital journeys, each one carrying us through different galactic neighborhoods, past different stellar landmarks under different patterns of stars. As we drift toward the end of our exploration of our cosmic address, it's worth reflecting on what this perspective offers us. We're not isolated wanderers in an empty universe, but citizens of a structured, organized galaxy, with neighborhoods and landmarks and a rich history. Our local arm may be minor compared to the galaxy's grand spiral highways, but it's home. It's where we belong, where we've always belonged, where the very atoms of our bodies were assembled over billions of years of stellar evolution. And as we continue our gentle journey outward from this intimate sense of galactic place, we'll next explore how these magnificent spiral arms came to exist in the first place. We'll discover the elegant physics that shapes our galaxy's architecture, the delicate balance of forces that creates and maintains these graceful stellar highways, and learn why spiral galaxies like ours are among the most beautiful and complex structures in the entire universe. Look at a nautilus shell, the delicate spiral of a fern unfurling, the graceful curve of a hurricane viewed from space, or the gentle swirl of cream stirred into coffee. Spirals appear everywhere in nature, from the microscopic to the cosmic, and there's something deeply satisfying about their geometry, something that speaks to a fundamental pattern woven into the fabric of the universe itself. Our galaxy is perhaps the most magnificent spiral of all, a cosmic pinwheel spanning 100,000 light-years. And tonight we're going to explore why it took this elegant shape and how it maintains its structure across billions of years. The ancient Greeks were fascinated by spirals, calling them sphaera, meaning coil or twist. They found spirals in seashells along Mediterranean beaches, in the horns of rams, in the way vines climb towards sunlight. The philosopher Archimedes studied them mathematically, discovering that a particular type of spiral increases its distance from the center at a constant rate as it turns. This Archimedean spiral appears throughout nature, from the arrangement of seeds in a sunflower to the arms of galaxies like our own. But why should a galaxy, a collection of hundreds of billions of stars scattered across vast distances, organize itself into such a graceful pattern? The answer lies in the delicate interplay between gravity, rotation, and time, a cosmic dance that has been unfolding for nearly the entire history of our universe. When our galaxy first formed, roughly 13 billion years ago, it began as a roughly spherical cloud of primordial gas and dark matter. This wasn't ordinary matter as we know it today, but a pristine mixture of hydrogen and helium, forged in the first few minutes after the Big Bang, laced with invisible dark matter that provided the gravitational scaffolding for structure to form. The dark matter, making up about 85% of the total mass, created a vast spherical halo that extends far beyond the visible stars we see today, a ghostly framework that still holds our galaxy together. As this cloud slowly collapsed under its own gravity, it began to spin, perhaps set in motion by the gravitational tugs of neighbouring matter or the turbulent flows of the early universe. The first stars to form in this collapsing cloud were giants unlike anything we see today, massive balls of pure hydrogen and helium that burned bright and died young. These population 3 stars, as astronomers call them, lived only a few million years before exploding as supernovae, scattering the first heavy elements into the pristine gas. And here's where the elegant physics begins. As the cloud contracted, it spun faster, just like a figure skater pulling in her arms during a spin. This conservation of angular momentum is one of the universe's most fundamental principles, and it shaped our galaxy's destiny. The spinning motion fought against the inward pull of gravity, creating a delicate balance that prevented the entire cloud from collapsing into a single massive black hole. This spinning, contracting cloud naturally flattened into a disk, the same way pizza dough spreads outward when spun by a skilled chef. The material in the outer regions, with more angular momentum to conserve, formed the extended disk we see today, while some of the gas fell inward toward the centre, creating the dense central bulge where older stars now cluster like a cosmic downtown. The transition from spherical halo to flattened disk took hundreds of millions of years, a gradual settling process that created the layered structure we observe today. But this still doesn't explain the spiral structure. A rotating disk of stars and gas should, by simple physics, remain relatively smooth and featureless. The spiral pattern requires something more subtle, more elegant than simple rotation. It requires what astronomers call density waves. Imagine traffic on a circular highway during rush hour. Cars travel at different speeds depending on the lane they're in, with inner lanes generally moving faster than outer ones. Now, imagine a slow-moving construction truck enters this highway. It creates a traffic jam, a region of higher density that moves around the highway much more slowly than any individual car. Cars approach the jam from behind, slow down as they pass through it, then speed up again once they're clear. The traffic jam itself persists and moves around the highway, even though it's constantly made up of different cars. This is remarkably similar to how spiral arms work in our galaxy. The spiral pattern itself rotates much more slowly than individual stars. Stars orbit the galactic center at different speeds depending on their distance from the center, but they all encounter the spiral density waves during their journeys. As stars move into a spiral arm, they slow down slightly due to the increased gravitational pull of all that extra matter. As they pass through and exit the other side, they speed up again. These density waves do more than just collect stars, though. They also compress the vast clouds of gas and dust that drift between the stars. And when gas gets compressed, magical things begin to happen. The increased density and pressure trigger the collapse of these clouds into stellar nurseries, regions where new stars are born in great abundance. This is why spiral arms appear so bright and prominent in photographs of galaxies. They're not just concentrations of existing stars, but active stellar maternity wards, where hot, young, blue stars are constantly being born. These massive blue giants burn brilliantly but briefly, living only a few million years before exploding as supernovae. They're so bright that they outshine all their older, more sedate neighbours, making the spiral arms glow with a distinctive blue-white light. The stellar nurseries within spiral arms are among the most beautiful and dynamic regions in our galaxy, cosmic cathedrals where the raw materials of space are transformed into blazing suns. These regions begin as vast, cold clouds of molecular hydrogen, carbon monoxide, and dust grains so fine they're smaller than the particles in cigarette smoke. The clouds can be enormous, stretching across hundreds of light years, yet they're so tenuous that they make the best vacuum chambers on Earth seem dense by comparison. When a spiral density wave compresses one of these molecular clouds, the physics becomes exquisite in its precision. The increased pressure causes the cloud to fragment into smaller, denser clumps, each potentially massive enough to ignite nuclear fusion. But the process isn't gentle. As gravity pulls the gas inward, the cloud begins to heat up and rotate faster. Magnetic fields thread through the collapsing material, sometimes supporting it against gravity, sometimes channeling material into bipolar jets that shoot outward at hundreds of kilometers per second. The Eagle Nebula, with its famous pillars of creation, lies within the Sagittarius Arm, a perfect example of this stellar birthing process in action. Those towering pillars, each several light years tall, are dense knots of gas and dust being sculpted by the intense radiation and stellar winds from nearby young stars. The pillars are simultaneously being destroyed by this energy and protected by it, as the dense material shields the gas behind it from the searing radiation. Within these protective cocoons, new stars are forming even now, hidden from our view, but detectable by infrared telescopes that can peer through the dust. The Orion Nebula, that fuzzy star in the sword of the constellation Orion that's visible to the naked eye on winter nights, tells a similar story but at a different stage. Here, the stellar nursery has already given birth to a cluster of hot young stars that have blown away much of their birth material, creating a glowing cavity in the surrounding molecular cloud. The four brightest stars at the nebula's heart, known as the trapezium, are less than 1 million years old, but already massive enough that their combined stellar winds are carving out this cosmic amphitheatre. These stellar nurseries operate on multiple scales simultaneously. The largest molecular clouds can spawn thousands of stars over millions of years, while smaller regions might produce only a handful of stellar siblings. The process is remarkably efficient. Despite the vast distances involved, gravity and magnetic fields work together to channel material across light years of space, concentrating it into stellar cores no larger than our solar system. It's a cosmic dance of construction and destruction, where the very act of star formation triggers feedback processes that can either encourage or suppress further stellar births in the surrounding region. When the most massive stars in these nurseries reach the end of their brief, brilliant lives, they explode as supernovae, sending shockwaves rippling through the surrounding gas. These explosions can trigger new waves of star formation by compressing nearby molecular clouds, but they can also disrupt the stellar nursery entirely, blowing away the remaining gas and ending the star-forming epoch. The result is a stellar cluster a gravitationally bound family of stars that will slowly drift apart over hundreds of millions of years as they orbit the galaxy. Ancient cultures often saw these bright patches along the Milky Way as significant landmarks. The Inca called the Coalsack Nebula, a dark cloud in the Southern Cross, the partridge, and used it as a calendar marker. Aboriginal Australians saw the same feature as the head of the emu in the sky. The bright star-forming region we call the Cygnus star cloud was known to Chinese astronomers as part of the Silver River, and marked an important crossing point in their celestial geography. What's remarkable about spiral density waves is their persistence. These patterns can maintain themselves for billions of years, far longer than any individual star's lifetime. The waves are sustained by the galaxy's rotation and the gravitational interactions between stars, gas, and the mysterious dark matter that provides the scaffolding for galactic structure. It's a self-organizing system, a cosmic mechanism that maintains order across vast scales of space and time. Different galaxies display different spiral patterns. Some, like the Whirlpool Galaxy, have two prominent arms that wrap around multiple times, creating a tightly wound spiral that looks almost like a cosmic rose. Others have more open, loosely wound arms or multiple arms that branch and merge. Our Milky Way appears to have four main spiral arms, though astronomers are still mapping their exact structure from our embedded perspective within the disk. The spiral pattern also changes over time. Computer simulations show that spiral arms can strengthen and weaken, that new arms can form while old ones fade away, and that the pattern can even flip, with trailing arms becoming leading arms under certain conditions. Our galaxy's current spiral structure may be quite different from what it looked like a billion years ago, and it will certainly evolve further over the billions of years to come. The density wave theory, developed in the 1960s by astronomers Lin and Xu, was one of the great triumphs of theoretical astrophysics. It explained not just why spiral galaxies exist, but why they're so common and so long-lived. Before this understanding, spiral arms were something of a mystery. Simple calculations showed that they should wind up and disappear within a few 100 million years as the inner parts of the galaxy rotated faster than the outer parts. The density wave theory revealed that the arms aren't material structures that wind up, but rather pressure waves that maintain their shape even as individual stars pass through them. This insight connected galactic astronomy to other areas of physics. The same mathematical framework that describes spiral density, waves in galaxies, also applies to Saturn's rings, where shepherd moons create spiral density waves that sculpt the ring material into delicate patterns. The physics appears at traffic flow on highways, in the formation of atmospheric jet streams, and in the spiral patterns of hurricanes. The spiral structure of our galaxy also plays a role in the distribution of heavy elements, the carbon, oxygen, and iron that make rocky planets and life possible. The shock fronts of spiral density waves can trigger not just star formation, but also the mixing of materials throughout the galactic disk. When massive stars in spiral arms explode as supernovae, they scatter these heavy elements into space, enriching the gas clouds that will form the next generation of stars and planets. This ongoing process of stellar death and rebirth concentrated in the spiral arms has gradually enriched our galaxy over billions of years. Early in the galaxy's history, stars were made almost entirely of hydrogen and helium. Today, thanks to countless cycles of star formation, stellar evolution, and supernova explosions, the interstellar medium contains all the elements necessary for complex chemistry and ultimately life. The spiral arms also serve as galactic highways for the transport of materials. Gas clouds can be channeled along the arms. carrying heavy elements from the inner galaxy outward, or funneling fuel from the outer regions toward the central black hole. These flows help regulate star formation throughout the galaxy and contribute to its ongoing evolution. Looking at spiral galaxies through powerful telescopes, astronomers have discovered that the spiral pattern often extends beyond the visible stars into the realm of neutral hydrogen gas. Radio telescopes can map this gas even when it's too cool and diffuse to form stars, revealing that the spiral structure persists far into the outer regions of galaxies where stars are sparse. The beauty of spiral galaxies isn't just aesthetic, it's functional. The spiral pattern is a cosmic engine, a mechanism for organizing matter and energy across vast scales, for triggering star formation and distributing heavy elements, for maintaining structure and complexity over billions of years. Without spiral density waves, our galaxy would be a much more boring, static place, and it's questionable whether the complex chemistry necessary for life would have had sufficient time and opportunity to develop. As you drift off tonight, perhaps you can carry with you this image of our cosmic home as a vast, elegant machine, a spiral engine that has been patiently crafting the elements of complexity for nearly the entire age of the universe. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were forged in stellar furnaces and scattered by supernovae explosions that occurred preferentially within these graceful spiral arms. You are, quite literally, made of spiral galaxy, a product of the same elegant physics that shapes hurricanes and nautilus shells, and the cream swirling in your morning coffee. And as we continue our journey through the architecture of our galactic home, we'll next explore the cities of stars themselves, the stellar populations that call these spiral arms home, and discover how different types of stars live and die and contribute to the ongoing story of our cosmic neighborhood. If you could shrink yourself down and wander through the Milky Way like a cosmic tourist, you'd discover that our galaxy isn't just a uniform collection of stars scattered randomly through space. Instead, it's more like a vast metropolis with distinct neighborhoods, each populated by different types of stellar citizens, with their own personalities, lifespans, and stories to tell. Tonight, let's take a gentle stroll through these stellar cities and meet the remarkable inhabitants that call our galaxy home. Just as human cities have their historic districts filled with grand old buildings and their modern suburbs populated by younger families, our galaxy has stellar populations that reflect different eras of cosmic history. Astronomers have learned to read the night sky like urban planners studying a city, identifying which stars are the ancient elders and which are the bright young newcomers by their chemical fingerprints and their neighborhoods of choice. The oldest residents of our galactic city live in what we might call the historic district, the central bulge and the vast spherical halo that surrounds our galaxy's disk. These are the population 2 stars, formed in the galaxy's youth when the universe was a simpler place, chemically speaking. They're made almost entirely of hydrogen and helium, with just tiny traces of heavier elements, because they were born before countless generations of massive stars had lived and died to enrich the cosmos with carbon, oxygen, iron, and all the other elements that make planets and people possible. These ancient stars are the cosmic equivalent of wise grandparents, moving slowly and deliberately through their neighborhoods. Many are red giants, stars that have exhausted the hydrogen fuel in their cores and expanded to enormous sizes, their surfaces cool and ruddy like autumn leaves. Others are white dwarfs, the compact remnants of stars that have already completed their life cycles, shining with the stored heat of their former glory, like cosmic embers slowly cooling in the dark. The globular clusters that orbit our galaxy's halo are perhaps the most remarkable neighborhoods in this ancient district. Imagine a spherical city containing hundreds of thousands of stars, packed into a region just a few dozen light-years across. From a planet within a globular cluster, the night sky would be a dazzling display of brightness, with stars close enough that the nearest neighbors would appear as brilliant points of light, casting shadows on the ground. These clusters are among the oldest structures in our galaxy, fossil remnants of the chaotic early epochs when the Milky Way was still taking shape. The Lakota people of North America looked at one of these clusters, which we call the Pleiades, and saw 7 sisters fleeing from a great bear. They told stories of how these tightly knit stars represented the importance of family bonds and staying together through difficult times. Without knowing the astronomy, they had intuited something profound about these stellar communities, recognizing them as cohesive groups that belonged together rather than random arrangements of unrelated stars. Moving inward from the ancient halo, we encounter the galactic disk, where a younger generation of stars has made their home. These population-run stars, including our own Sun, were born from gas clouds that had been enriched by the deaths of earlier stellar generations. They're the cosmic middle class, containing enough heavy elements to form rocky planets, complex molecules, and all the chemistry that makes life possible. The disk is further subdivided into neighborhoods with their own distinct characteristics. The thin disk, where we live, is the bustling downtown of star formation, home to the galaxy's youngest and most energetic residents. Here you'll find the stellar equivalent of artists and innovators, hot blue giants that burn bright and live fast, dying in spectacular supernova explosions after just a few million years. These massive stars are the cosmic celebrities, outshining all their neighbors but leading brief, dramatic lives that end in explosive glory. Between these stellar extremes live the steady, reliable citizens like our Sun, middle-aged yellow stars that burn their nuclear fuel at a measured pace, providing stable energy for billions of years. These are the stars most likely to host planetary systems with complex chemistry and perhaps even life. They're not the most spectacular residents of the galactic city, but they're the dependable ones, the cosmic equivalent of the teachers and engineers and nurses who keep civilization running smoothly. The thick disk, lying above and below the thin disk, houses an intermediate population of stars that are older and more sedate than their thin disk cousins, but younger than the ancient halo dwellers. These stars follow more eccentric orbits, carrying them farther above and below the galactic plane in their journeys around the galaxy's center. They're like the suburban commuters of our cosmic city, traveling greater distances but maintaining their connection to the bustling central neighborhoods. Within the spiral arms themselves, we find the galaxy's most active construction zones, the stellar nurseries where new citizens are constantly being born. These regions are painted in the brilliant colors of hot young stars and the glowing gas clouds they illuminate. The red glow comes from hydrogen gas energized by nearby stars, while blue regions indicate areas where starlight reflects off dust grains in the stellar birth clouds. The star-forming regions have their own ecology, a complex interplay of creation and destruction. The most massive newborns, the O and B type stars, shine with blue-white brilliance but live such intense lives that they burn out in just a few million years. When they die, they explode as supernovae, sending shock waves rippling through their neighborhoods. These explosions can trigger new waves of star formation by compressing nearby gas clouds, but they can also disrupt stellar nurseries entirely, blowing away the raw materials needed for future stellar births. Ancient Chinese astronomers divided their sky into 28 lunar mansions, recognizing that different regions had different characteristics and stellar populations. They noted that some areas were rich in bright blue stars, while others were dominated by older, redder suns. Without understanding stellar evolution, they had mapped the galaxy's demographic patterns, identifying the cosmic neighborhoods just as we do today with our modern telescopes and spectrographs. The chemical composition of stars tells the story of our galaxy's enrichment over time. The earliest stars were cosmic pioneers, exploring a universe that contained only the lightest elements. When they died, they scattered heavier elements into space, seeding the gas clouds that would form the next generation of stars. This process has continued for billions of years, gradually enriching our galaxy with the full periodic table of elements. Each stellar generation is slightly more metal-rich than the last, using the astronomers' definition of metals as any element heavier than hydrogen and helium. By measuring the metallicity of stars, astronomers can determine their approximate age and trace the chemical evolution of our galaxy. It's like reading the rings of a cosmic tree, with each stellar population recording the conditions present when it formed. The stellar populations also reveal the dynamic history of our galaxy. Some stars in the halo show signs of having been captured from smaller galaxies that the Milky Way has consumed over its lifetime. These stellar immigrants carry the chemical signatures of their birth galaxies, preserving evidence of ancient cosmic mergers and acquisitions. The Sagittarius dwarf galaxy is currently being torn apart by our galaxy's gravity, its stars slowly joining our halo population in a process that will take hundreds of millions of years to complete. Brown dwarfs occupy a special place in our stellar taxonomy, objects too massive to be planets but too small to sustain nuclear fusion like true stars. These failed stars glow with the heat of their formation but slowly cool and fade over billions of years. They're the cosmic equivalents of those mysterious neighbours who keep to themselves, visible only to infrared telescopes that can detect their faint heat signatures. At the other extreme are the stellar giants, red supergiants like Betelgeuse in Orion, that have swollen to enormous sizes as they approach the end of their lives. If Betelgeuse were placed at the centre of our solar system, its surface would extend beyond the orbit of Mars. These stellar leviathans are cosmic time bombs, destined to explode as supernovae when their nuclear fuel runs out, events so energetic they can briefly outshine entire galaxies. The stellar cities of our galaxy are connected by invisible highways of gravitational influence and chemical exchange. Stellar winds from massive stars carry enriched material throughout the galaxy, while supernova explosions create bubbles of hot gas that can extend for hundreds of light years. These processes mix and redistribute the heavy elements produced in stellar cores, ensuring that each new generation of stars is born from material enriched by its predecessors. Binary and multiple star systems represent the cosmic equivalent of stellar families, gravitationally bound partners that orbit around their common centre of mass. About half of all stars in our galaxy belong to such systems, dancing cosmic waltzes that can last for billions of years. Some binaries are so close that material flows from one star to the other, creating spectacular light shows as the transferred matter heats up and glows. Others are widely separated, their connection apparent only through careful observation of their orbital motion over many years. The stellar neighbourhood around our Sun contains a representative sample of our galaxy's citizens. Within about 30 light-years of Earth we can find red dwarfs that will burn steadily for trillions of years, white dwarfs that represent the final fate of Sun-like stars, and even a few binary systems where stellar partners orbit each other in periods measured in decades. This local stellar census helps astronomers understand the demographics of the galaxy as a whole, providing a detailed sample of stellar types and behaviors. Variable stars add rhythm to our cosmic city, pulsating in brightness with periods ranging from hours to years. The Cepheid variables, yellow supergiants that brighten and dim with clockwork regularity, served as cosmic lighthouses that helped astronomers first measure the true scale of our galaxy and discover the existence of other galaxies beyond our own. These stellar beacons still serve as standard candles, their predictable brightness variations allowing us to measure distances across the cosmos. As we drift through these stellar neighborhoods in our imagination, we begin to appreciate the incredible diversity of our galactic home. From ancient red giants that remember the galaxy's youth, to brilliant young stars still surrounded by their birth clouds. From failed brown dwarfs to stellar giants destined for explosive ends, our cosmic city contains multitudes. Each star is a world unto itself, with its own history, personality, and destiny, yet all are connected by the gravitational bonds and chemical heritage that make them citizens of the same galactic community. The beauty of this stellar taxonomy lies not just in its scientific precision, but in its revelation of cosmic time and connection. We are made of material processed through generations of stellar lives and deaths, our atoms forged in the nuclear furnaces of stars that lived and died long before our solar system existed. We are citizens of this stellar city in the most literal sense, products of its long history and inheritors of its chemical legacy. And as we prepare to explore how this magnificent stellar city moves through space, how it dances its slow cosmic dance around the galactic center, we carry with us an appreciation for the diverse community of stellar neighbors that shares this journey. From the ancient wisdom of population 2 elders to the bright promise of newly formed stars, we are all passengers on the same galactic voyage, all participants in the same grand cosmic story that began 13 billion years ago and continues to unfold in the stellar cities of the Milky Way. Right now, as you listen to these words, you're participating in one of the most elegant dances in the universe. You might feel perfectly still, comfortably settled wherever you are, but you're actually spinning with Earth at over 1,600 kilometers per hour at the equator. More remarkably, you're racing through space at 220 kilometers per second as our entire solar system orbits the center of the Milky Way. That's fast enough to travel from New York to Los Angeles in about 20 seconds, yet the dance is so smooth, so perfectly choreographed, that you can't feel the motion at all. This is the slow cosmic dance of our galaxy, a gravitational ballet that has been unfolding for billions of years. Every star, every planet, every grain of cosmic dust participates in this grand orbital symphony, each following its own path while contributing to the larger pattern. Tonight, let's explore this magnificent choreography and discover how our solar system has been waltzing through the galaxy since long before Earth had continents or oceans or any life at all. The ancient Greeks noticed that the stars seemed fixed in their patterns relative to each other, leading them to call them fixed stars in contrast to the wandering planets. They couldn't have imagined that all those apparently stationary points of light were actually racing through space at hundreds of kilometers per second, their motion imperceptible only because of the vast distances involved. It's like watching distant mountains from a moving car. They appear motionless even though you know you're traveling at highway speeds. But our galaxy isn't a solid wheel spinning as a single unit. Instead, it rotates differentially, with different parts moving at different speeds, depending on their distance from the galactic center. This creates what astronomers call the galaxy's rotation curve, a beautiful demonstration of how gravity orchestrates motion across cosmic scales. Near the galactic center, stars orbit relatively quickly, whipping around the central supermassive black hole in periods measured in years or decades. These inner-city residents live life in the fast lane, their high-speed orbits necessary to maintain their positions against the intense gravitational pull of the galaxy's dense core. Some stars venture so close to our galaxy's central black hole that they complete their orbits in just 16 years, travelling at a significant fraction of the speed of light during their closest approach. As we move outward from the centre, the orbital speeds initially decrease, following the same pattern we see in our solar system, where Mercury races around the Sun much faster than distant Pluto. But something strange happens in the outer regions of galaxies. Instead of continuing to slow down as expected, the orbital speeds level off and remain roughly constant even at the galaxy's edge. This flat rotation curve was one of the first major pieces of evidence for the existence of dark matter, that mysterious substance that makes up about 85% of the galaxy's total mass. Our solar system sits in what might be called the galactic suburbs, about 26,000 light-years from the centre, where we orbit at a leisurely 220 kilometers per second. This might sound fast, but it's actually a comfortable cruising speed by galactic standards. We're moving fast enough to resist falling toward the galactic centre, but not so fast that we'd escape the galaxy's gravitational embrace entirely. At this speed, it takes our solar system approximately 225 million years to complete one orbit around the galaxy's centre. Astronomers call this period a galactic year, and it provides a wonderfully grand perspective on Earth's history. Since our planet formed 4.6 billion years ago, we've completed roughly 20 galactic orbits. When the dinosaurs ruled the Earth, we were on the opposite side of the galaxy from where we are today. The last time our solar system was in its current galactic position, the most complex life forms on Earth were simple marine organisms just beginning to develop hard shells. The Maya understood cyclical time in ways that modern astronomy has validated on a cosmic scale. Their complex calendar system recognized that time moves in nested cycles, with smaller patterns embedded within larger ones, stretching from daily rhythms to periods spanning thousands of years. They couldn't have known about galactic years, but they grasped intuitively that the universe operates on multiple timescales simultaneously, with celestial cycles far grander than human experience. As our solar system orbits the galaxy, we don't follow a perfect circle, but rather a slightly elliptical path that carries us closer to and farther from the galactic center over time. We also bob up and down relative to the galactic plane, oscillating above and below the disk's midline with a period of about 60 million years. This vertical motion is caused by the gravitational influence of the disk's mass, which acts like a gentle restoring force, pulling us back toward the galactic equator whenever we drift too far above or below it. This bobbing motion has led some scientists to speculate about connections between our galactic position and Earth's climate history. When we pass through the denser regions of the galactic disk, we encounter more interstellar dust and gas, which could affect the amount of cosmic radiation reaching our solar system. Some researchers have proposed that passages through spiral arms or the galactic plane might correlate with ice ages or mass extinction events, though the evidence for such connections remains hotly debated. The spiral arms themselves add another layer of complexity to our galactic journey. Remember that these arms aren't fixed structures, but rather density waves that rotate more slowly than the stars within them. This means that during our 225 million year orbit, We periodically enter and exit different spiral arms, spending roughly 100 million years in each arm and about the same amount of time in the quieter regions between them. Currently, we're located in the Orion Arm, a minor spiral structure between the major Perseus and Sagittarius arms. But over the course of Earth's history, we've experienced many different galactic neighborhoods. Sometimes we've traveled through the bustling stellar cities of major spiral arms, where bright young stars and active stellar nurseries filled the local environment with higher levels of radiation and more frequent supernova explosions. Other times we've cruised through the quieter galactic countryside between arms, where the stellar density is lower and the cosmic environment more peaceful. Aboriginal Australian cultures developed sophisticated understanding of cyclical time, recognizing patterns that operate on scales from seasonal to generational. Their Dreamtime concept encompasses both the creation period and an ongoing present, where ancestral beings continue to influence the world through recurring patterns and cycles. This cyclical worldview resonates with our modern understanding of galactic motion, where our solar system traces the same general orbital path repeatedly while encountering slightly different conditions each time. The gravitational forces that govern our galactic orbit are the same ones that keep planets circling the Sun and Moon's orbiting planets, but they operate on incomparably larger scales. The central supermassive black hole, weighing in at about 4 million times the mass of our Sun, provides a gravitational anchor that helps organize the inner regions of the galaxy. But the majority of the gravitational pull we feel comes from the combined mass of hundreds of billions of stars and the vast halo of dark matter that surrounds our galaxy. Dark matter remains one of astronomy's greatest mysteries, detectable only through its gravitational effects on visible matter. In our galaxy, dark matter creates an extended spherical halo that provides the gravitational scaffolding for the entire structure. Without this invisible mass, the outer regions of the galactic disk would not rotate as quickly as they do, and the galaxy as we know it simply couldn't exist. The interplay between visible and dark matter creates a gravitational environment that has remained remarkably stable for billions of years. This stability is one of the reasons life was able to evolve and flourish on Earth. In a more chaotic galactic environment, with frequent close encounters with massive stars or passages through dense molecular clouds, our planet's biosphere might have been repeatedly disrupted by radiation or gravitational disturbances. As we orbit the galaxy, we're not alone in our journey. The entire solar system moves as a coherent unit, with all the planets, moons, asteroids, and comets maintaining their relative positions while participating in the greater galactic dance. It's like a family of dancers moving together across a vast ballroom, each maintaining their own internal choreography while participating in the larger pattern. The local standard of rest provides astronomers with a reference frame for measuring stellar motions within our galactic neighborhood. This represents the average motion of nearby stars, a kind of cosmic baseline that helps us understand how individual stars deviate from the general galactic rotation pattern. Our Sun moves at about 20 kilometers per second relative to this local standard, drifting slowly toward the constellation Hercules as it orbits the galaxy. Ancient Persian astronomers developed sophisticated models of planetary motion that recognized the importance of reference frames and relative motion. They understood that the apparent complexity of planetary paths could be simplified by choosing the right perspective, a principle that applies equally well to understanding stellar motion within our galaxy. From our embedded position within the galactic disk, stellar motions appear complex and seemingly random, but from a perspective outside the galaxy, the elegant orbital patterns would become clear. The galactic rotation also creates what astronomers call differential motion, where stars at slightly different distances from the galactic center have slightly different orbital periods. This causes stellar associations and open star clusters to gradually spread out over time as stars born together in the same molecular cloud slowly drift apart in their individual orbits. The Hyades and Pleiades star clusters are examples of such gravitationally bound groups, though they will eventually disperse as the differential rotation of the galaxy pulls their member stars into slightly different orbital paths. Our galactic orbit carries us through regions of varying stellar density and composition. Sometimes we travel through areas rich in massive young stars that flood the local environment with intense ultraviolet radiation. Other times we pass through regions populated mainly by older, cooler stars that provide a more benign radiation environment. These variations in our cosmic neighborhood might have subtle effects on Earth's climate and atmosphere over geological timescales. The Milky Way's rotation also drives a complex circulation pattern in the interstellar medium, the thin gas and dust that fills the space between stars. Hot bubbles created by supernova explosions rise above and below the galactic plane, while cooler gas sinks back toward the disk. This galactic fountain effect helps distribute heavy elements throughout the galaxy and plays a crucial role in regulating star formation rates in different regions. Looking toward the future, our galactic dance will continue for billions of years to come, though it won't remain exactly the same. The Milky Way is slowly consuming smaller nearby galaxies, adding their mass to our own and subtly altering the gravitational environment. In about 4.5 billion years, we'll experience a much more dramatic change when the Andromeda Galaxy arrives for a cosmic collision that will fundamentally reshape both galaxies. But for now, we continue our stately progression around the galactic center, completing our 225 million year orbit with metronomic precision. The dance is so perfectly choreographed that from our perspective, it feels like stillness. The stars maintain their familiar patterns in our night sky, the seasons cycle with dependable regularity, and life continues its own intricate dance on our small blue planet. As you settle into sleep tonight, you can carry with you the knowledge that you're part of this magnificent cosmic choreography. You're spinning with Earth, racing through space with the solar system, orbiting the galactic center at tremendous speed, all while participating in the slow, graceful dance that has been unfolding since the galaxy's formation. It's a dance that connects you to every star in the night sky, every distant nebula, every cosmic process that has ever occurred within our galactic home. And as we continue our exploration of this grand orbital ballet, we'll next discover how our journey through different galactic neighborhoods has influenced our planet's history, how passages through spiral arms and encounters with molecular clouds have left their marks on Earth's geological and biological record, weaving our local story into the vast narrative of our galactic voyage. Imagine you could watch Earth from space across the vast span of geological time, witnessing the slow waltz our planet has danced through the galaxy for the past 4.6 billion years. You would see our blue world threading its way through spiral arms and interarm regions, bobbing up and down through the galactic plane like a gentle rider on cosmic waves. Sometimes we've journeyed through the bright, bustling neighborhoods of major spiral arms, where massive stars paint the darkness with their brilliant light. Other times we've drifted through the quieter spaces between arms, where the stellar population thins out and the cosmic environment grows more peaceful. This galactic journey hasn't been merely a scenic tour through space. Each passage has potentially left subtle fingerprints on our planet's climate, geology, and the long story of life itself. Tonight, let's explore how our cosmic wanderings might have influenced Earth's history, weaving together the grand narrative of galactic astronomy with the intimate story of our own world. The relationship between our galactic position and Earth's history operates on timescales that dwarf human experience. While we orbit the galactic center once every 225 million years, the spiral arms themselves rotate more slowly, creating a complex pattern of encounters and departures that has shaped our cosmic neighborhood throughout Earth's existence. It's like living in a city where the neighborhoods themselves slowly rotate, so that over the centuries your house encounters different districts with their own unique characters and influences. During our planet's long history, we've passed through the major spiral arms roughly every 100 to 150 million years. Each passage has exposed our solar system to different conditions: higher stellar densities, more frequent supernova explosions, increased cosmic ray exposure, and encounters with giant molecular clouds. These cosmic environmental changes operate on such vast timescales that their effects, if they exist, would be woven into the very fabric of Earth's geological and biological record. The ancient Chinese developed sophisticated astronomical records that tracked celestial events across centuries, recognizing that the heavens operated on cycles far longer than human lifetimes. Their imperial astronomers maintained continuous observations for over 2 millennia, creating one of the longest unbroken records of cosmic phenomena in human history. They understood intuitively what modern astronomy has confirmed: that celestial influences operate on multiple time scales, from daily and seasonal rhythms to grand cycles spanning geological ages. One of the most intriguing possibilities is that passages through spiral arms might correlate with some of Earth's major ice ages. When our solar system travels through the dense stellar regions of spiral arms, we encounter higher concentrations of interstellar dust and gas. This material, swept up by our solar system's motion through space, could potentially affect the amount of solar radiation reaching Earth's surface. Some researchers have proposed that this cosmic dust might trigger ice ages by reducing the solar energy that warms our planet. The geological record shows that Earth has experienced several major ice ages throughout its history, periods when vast ice sheets covered much of the continents and global temperatures dropped significantly. The most recent ice age began about 2.6 million years ago and included the glacial periods that carved out the Great Lakes and sculpted the landscapes of northern Europe and North America. While these relatively recent glaciations are well explained by changes in Earth's orbit and tilt, the deeper ice ages in Earth's history might have cosmic connections. The Permian-Triassic extinction event, which occurred about 252 million years ago and eliminated roughly 90% of marine species, happened during a period when our solar system might have been passing through or near a major spiral arm. This great dying was the most severe extinction in Earth's history, far more devastating than the asteroid impact that ended the dinosaurs 66 million years ago. While the primary cause was likely massive volcanic eruptions in Siberia, some scientists speculate that cosmic factors might have contributed to the severity of the crisis. Indigenous Australian cultures maintained oral traditions spanning tens of thousands of years, preserving knowledge of environmental changes that occurred on timescales far exceeding individual human memory. Their Dreamtime stories encode information about sea level changes, climate shifts, and landscape transformations that modern science has confirmed through geological evidence. This demonstrates humanity's capacity to perceive and remember patterns that operate on extended timescales, even without written records or scientific instruments. The concept of a galactic habitable zone adds another layer to our understanding of cosmic influences on Earth's habitability. Just as planets must orbit at the right distance from their stars to maintain liquid water, solar systems may need to orbit at optimal distances from their galactic centers to support complex life over billions of years. Too close to the galactic center, and frequent supernova explosions and high radiation levels could sterilize planetary surfaces. Too far out in the galactic suburbs, and there might not be enough heavy elements to form rocky planets in the first place. Our current position, about 26,000 light-years from the galactic center, places us in what appears to be a cosmic sweet spot. We're far enough from the dense central regions to avoid the most disruptive astronomical events, yet close enough to benefit from the heavy element enrichment that comes from generations of stellar evolution. This Goldilocks zone of galactic real estate might be one of the reasons Earth has remained habitable for billions of years. The vertical oscillation of our solar system above and below the galactic plane adds another dimension to our cosmic journey. Every 30 to 35 million years, we pass through the relatively dense midplane of the galaxy, where we encounter higher concentrations of interstellar matter and potentially disruptive gravitational influences. Some researchers have proposed that these plane crossings might correlate with periodic extinction events in Earth's fossil record, though the evidence remains controversial. During plane crossings, our solar system encounters the galactic disk's gravitational field more directly, which could perturb the orbits of comets in the distant Oort cloud. This gravitational stirring might send showers of comets toward the inner solar system, increasing the risk of impacts on Earth and other planets. The hypothesis suggests a roughly 26 million year cycle of increased extinction rates, though many paleontologists question whether such a regular pattern actually exists in the fossil record. Cosmic rays, high-energy particles that stream through space from distant astronomical sources, provide another potential link between our galactic environment and Earth's history. When we pass through spiral arms with their higher densities of massive stars and supernova remnants, the cosmic ray flux reaching our solar system increases significantly. These particles can penetrate Earth's atmosphere and potentially affect cloud formation, climate patterns, and even the mutation rates that drive biological evolution. The magnetic field generated by Earth's molten iron core provides crucial protection against cosmic radiation, but this shield has varied in strength throughout our planet's history. During periods when the magnetic field was weak or reversed, enhanced cosmic ray exposure during spiral arm passages might have had more pronounced effects on Earth's atmosphere and biosphere. Some scientists have speculated that increased cosmic ray exposure could have contributed to evolutionary pressures that drove periods of rapid biological change. Tree ring studies and ice core records have revealed that Earth's climate system responds to various cosmic influences, from solar activity cycles to changes in cosmic ray flux. While these effects are typically small compared to internal climate drivers like volcanic eruptions or greenhouse gas changes, they demonstrate that our planet exists within a larger cosmic environment that subtly influences terrestrial conditions. The Mayan civilization developed remarkably accurate astronomical calendars that tracked celestial cycles spanning thousands of years. Their long count calendar attempted to place human history within cosmic timescales, recognizing that earthly events occurred against a backdrop of vast celestial rhythms. While they couldn't have known about galactic rotation or spiral arm passages, Their calendrical systems reflected an intuitive understanding that cosmic and terrestrial time are intimately connected. Molecular clouds, the stellar nurseries where new stars are born, present another potential influence on Earth's environment during our galactic travels. These vast structures can extend across hundreds of light years and contain enough material to form thousands of stars. When our solar system passes through or near such clouds, the increased density of interstellar matter could affect the heliosphere, the bubble of charged particles that the Sun blows around our solar system. Changes in the heliosphere's size and strength could alter the amount of galactic cosmic radiation reaching Earth's atmosphere. During encounters with dense molecular clouds, the heliosphere might shrink, allowing more cosmic rays to penetrate the inner solar system. Conversely, during passages through less dense regions between spiral arms, the heliosphere might expand, providing enhanced protection from cosmic radiation. The geological record of Earth contains potential signatures of these cosmic influences, though they're often subtle and difficult to distinguish from terrestrial causes. Isotopic ratios in ancient rocks, patterns in the fossil record, and geochemical signatures in ice cores all provide windows into Earth's past environmental conditions. Some researchers have claimed to find correlations between these terrestrial records and calculated timing of spiral arm passages, though the evidence remains hotly debated within the scientific community. Looking forward, our continued galactic journey will expose Earth to new cosmic environments over the coming millions and billions of years. In about 30 million years, we'll complete our current passage through the Orion Arm and enter the relatively quiet region between the Orion and Perseus arms. This transition might bring subtle changes to our cosmic radiation environment and the density of interstellar matter in our solar system's vicinity. The relationship between galactic position and planetary habitability remains an active area of research, with implications extending far beyond our own solar system, as astronomers discover thousands of exoplanets orbiting other stars. Understanding how galactic environment affects planetary habitability becomes crucial for assessing the potential for life elsewhere in the universe. Planets in the galactic center regions might face very different challenges than those in the outer spiral arms or the sparse regions between galaxies. Ancient Polynesian navigators developed sophisticated wayfinding techniques that relied on reading subtle environmental cues across vast ocean distances. They understood that navigation required awareness of multiple interconnected systems, ocean currents, wind patterns, star positions, and wildlife behavior, all provided information about location and direction. Similarly, understanding Earth's position within galactic currents and environmental gradients provides context for our planet's long-term habitability and evolutionary history. The story of Earth's passages through galactic time reveals our planet as more than an isolated world orbiting a single star. We are cosmic travelers, embedded within galactic currents and environmental gradients that have subtly influenced our world's development over billions of years. Whether these cosmic influences have significantly shaped Earth's climate and biological evolution remains an open question, but the possibility reminds us that we are citizens of the galaxy in ways both profound and practical. As we drift toward dawn and the completion of tonight's galactic journey, we carry with us a new perspective on Earth's place in cosmic time. Our blue world is not separate from the galaxy that contains it, but rather an integral part of galactic processes that operate on scales far grander than continents shifting or mountains rising. We are passengers on a planet that has been sailing through cosmic seas for billions of years, encountering different stellar weather patterns and cosmic climates as it follows its ancient orbital path through the slowly turning spiral of our galactic home. And as we prepare to meet our galactic neighbours, to explore the community of galaxies that surrounds the Milky Way, we take with us this understanding of cosmic time and terrestrial connection, this appreciation for the deep rhythms that connect the smallest details of Earth's history to the grandest patterns of galactic evolution. Step outside on a clear autumn evening and look toward the constellation Andromeda. With your naked eye, you might just barely make out a faint, fuzzy patch of light, no bigger than a smudge on the cosmic window. What you're seeing is an entire galaxy, a collection of over 1 trillion stars stretching across 220,000 light-years of space. The Andromeda Galaxy is our nearest major galactic neighbour, and right now, as you gaze up at it, it's racing toward us through the cosmic darkness at 250,000 miles per hour. This might sound alarming, but the approach is so stately, so magnificently slow by cosmic standards, that the collision won't occur for another 4.5 billion years. By then, our sun will have swollen into a red giant, and Earth's story will have taken many unexpected turns. The galaxies will merge not in a violent crash, but in a graceful gravitational dance, their spiral arms intertwining like cosmic partners in an eternal waltz. Our galactic neighbourhood, known to astronomers as the Local Group, is a gravitationally bound collection of more than 80 galaxies scattered across roughly 10 million light-years of space. It's a cosmic village where the Milky Way and Andromeda serve as the two largest residents, while dozens of smaller dwarf galaxies orbit around them like cosmic suburbs and satellite towns. The ancient Arab astronomers called that fuzzy patch in Andromeda the Little Cloud, Al-Sufi describing it in his Book of Fixed Stars over 1,000 years ago. They couldn't have imagined they were looking at an entire universe of stars, a cosmic island so vast that light takes over 2 million years to cross from one side to the other. To them, it was simply another mystery in the night sky, one more puzzle in the grand tapestry of celestial lights. The Local Group tells a story of cosmic community, of gravitational relationships that bind galaxies together across vast distances. Just as cities have their downtown cores and suburban sprawl, our galactic neighbourhood has its own structure and hierarchy. The Milky Way and Andromeda anchor the group with their massive gravitational influence, while smaller galaxies like the Magellanic Clouds, the Triangulum Galaxy, and dozens of dwarf spheroidal and elliptical galaxies complete our cosmic community. The Magellanic Clouds, visible as hazy patches in the southern hemisphere sky, are perhaps our most familiar galactic neighbours. These irregular dwarf galaxies have been gravitationally bound to the Milky Way for billions of years, orbiting us like cosmic moons. The large Magellanic Cloud contains about 30 billion stars, while its smaller companion holds roughly 7 billion. To observers in the southern hemisphere, they appear as detached pieces of the Milky Way, bright patches of starlight that have inspired myths and navigation stories for countless generations. Australian Aboriginal cultures wove the Magellanic Clouds into their Dreamtime stories, seeing them as campfires of the ancestors, or as celestial waterholes where the spirits of the departed would gather. Polynesian navigators used them as stellar compasses during their epic ocean voyages. Understanding their movements across the night sky well enough to navigate thousands of miles of open ocean with remarkable precision, these navigators couldn't have known they were using entire galaxies as their guide stars, but they recognized their reliability and cosmic significance. The gravitational interactions between the Milky Way and the Magellanic Clouds have created one of the most beautiful structures in our local cosmic neighbourhood, the Magellanic Stream. This is a vast river of hydrogen gas stretching across 200 degrees of sky, material that has been tidally stripped from the clouds during their orbital dance around our galaxy. Radio telescopes reveal this stream as a ghostly trail following the clouds in their orbit, a cosmic wake left by their passage through the outer reaches of our galaxy's gravitational influence. Dark matter plays a crucial role in holding our local group together, providing the invisible gravitational scaffolding that prevents the member galaxies from drifting apart into the expanding universe. Computer simulations show that without dark matter, the local group would have dispersed long ago, its galaxies scattered by cosmic expansion like leaves in an autumn wind. The dark matter halos surrounding each galaxy extend far beyond their visible boundaries, creating a web of gravitational connections that bind the group together. The Triangulum Galaxy, our third largest local group member, presents its own unique character. This face-on spiral galaxy gives us a preview of what our eventual merger with Andromeda might look like from the outside. Its spiral arms are looser and more open than ours, painted with bright pink star-forming regions where massive young stars illuminate the surrounding gas clouds. At about 3 million light-years away, Triangulum is distant enough that we can appreciate its full spiral structure, yet close enough to study individual stellar populations within its disk. Ancient Chinese astronomers maintained careful records of what they called guest stars, sudden appearances of new lights in the sky that we now know were supernovae in nearby galaxies. They couldn't have realized they were witnessing stellar explosions in distant galactic neighbors, but they recognized these events as significant cosmic phenomena, worthy of detailed observation and record-keeping. The meticulous documentation now helps modern astronomers study the historical behavior of stars in our local group neighbors. The dwarf galaxies that populate our cosmic neighborhood come in several varieties, each telling its own story of galactic evolution. Dwarf elliptical galaxies are smooth, round collections of old stars with little ongoing star formation. They're like cosmic retirement communities, populated by ancient red and yellow stars that have long since exhausted their capacity for vigorous stellar birth. Dwarf irregular galaxies, by contrast, are messy collections of gas, dust and stars still actively forming new stellar generations in chaotic, unstructured patterns. Some of the most intriguing local group members are the ultra-faint dwarf galaxies, so sparse and dim that they were only discovered in recent decades through careful analysis of large-scale sky surveys. These ghostly structures contain only a few thousand stars scattered across regions hundreds of light-years wide, making them among the least dense objects in the universe. They're held together primarily by dark matter, with the visible stars serving almost as tracers for the invisible mass that dominates their structure. The discovery of these ultra-faint dwarfs has revolutionized our understanding of galaxy formation and dark matter physics. They represent the smallest, most dark matter-dominated galaxies known, providing crucial tests for theories about how structure forms in the universe. Some contain so little ordinary matter that they're essentially dark matter halos, with just a handful of stars sprinkled throughout, cosmic ghosts that barely register against the night sky. Our local group galaxies are not isolated islands, but rather participants in larger cosmic currents. The entire group is falling toward the Virgo cluster, a massive collection of over 1,300 galaxies located about 54 million light-years away. This motion carries us at hundreds of kilometers per second through the cosmic web, the large-scale structure that organizes matter throughout the observable universe. The gravitational influence of the Virgo cluster creates what astronomers call the Virgo infall, a cosmic river that draws local group and thousands of other nearby galaxies toward this massive galactic metropolis. It's like living in a small town that's part of a larger regional economy, connected to distant urban centres through transportation networks and economic flows that operate on scales far larger than the local community. The approaching merger between the Milky Way and Andromeda, sometimes dubbed Milkomeda by astronomers, will be one of the most spectacular events in our cosmic neighbourhood's future. Computer simulations show that the merger will likely trigger intense bursts of star formation as gas clouds in both galaxies collide and compress. The combined galaxy will probably evolve into a giant elliptical, losing the delicate spiral structure that currently defines both partners. During the merger, individual stars will rarely collide due to the vast distances between them, but their orbits will be dramatically reorganized by the changing gravitational field. Our solar system might be flung to the outer regions of the merged galaxy, or it might spiral inward toward the new central core. The night sky will be transformed as the familiar constellations are scattered, and the combined light of two galactic cores illuminates the cosmic landscape. Tibetan Buddhist astronomy recognized the interconnectedness of celestial phenomena, understanding that apparently separate objects in the sky were part of larger patterns and relationships. Their cosmological models emphasize cycles within cycles, connections between different scales of existence, and the importance of understanding one's place within the larger cosmic order. This perspective resonates with modern understanding of how galaxies relate to each other within groups, clusters, and the broader cosmic web. The local group provides a natural laboratory for studying galaxy evolution, stellar populations, and dark matter physics. Because these galaxies are relatively nearby, astronomers can resolve individual stars and study their properties in detail. The Hubble Space Telescope has mapped stellar populations in many local group galaxies, revealing their star formation histories and chemical evolution over billions of years. These studies show that galaxy evolution is not a solitary process, but rather a community affair, with neighbouring galaxies influencing each other through gravitational interactions, stellar feedback, and the exchange of gas and dust. Small galaxies can be disrupted by close encounters with larger ones, their stars scattered into extended tidal streams that trace their orbital histories. Larger galaxies grow partly by accreting these smaller companions, a process that continues today as we observe the ongoing disruption of the Sagittarius dwarf galaxy by our own Milky Way. The chemical compositions of local group galaxies reveal the history of stellar nuclear synthesis and element distribution on cosmic scales. Each galaxy has processed hydrogen and helium into heavier elements at different rates and through different pathways, creating a diverse chemical inventory that reflects their individual evolutionary histories. Comparing these chemical fingerprints helps astronomers understand how galaxies form, evolve, and interact over cosmic time. Looking beyond our local group, we can see other galaxy groups and clusters scattered throughout the observable universe, each representing a different experiment in cosmic structure formation. Some groups are young and still assembling, their member galaxies streaming toward each other through the cosmic web. Others are ancient and mature, their galaxies having undergone multiple merger events and settled into stable configurations. The study of local group dynamics also provides insights into the nature of dark matter and dark energy, the mysterious components that dominate the universe's mass-energy budget. The motions of galaxies within the group, their internal structure, and their response to external gravitational fields all provide clues about the properties of these invisible cosmic constituents. As we prepare to conclude our gentle journey through our galactic home and its cosmic neighborhood, we can appreciate how our local group represents both community and destiny. We are not alone in the cosmic darkness, but rather part of a gravitationally bound family of galaxies, each with its own character and story, all participating in the slow dance of cosmic evolution. The approaching merger with Andromeda reminds us that even on the largest scales, the universe is dynamic and evolving. Our galactic neighborhood will not remain the same forever, but will continue to change and develop over billions of years, creating new structures and relationships in the ongoing story of cosmic evolution. Tonight, as you look up at the stars, you can know that you're seeing not just our own galactic home, but glimpses of our cosmic neighbours as well. The faint glow of the Magellanic Clouds, the barely visible smudge of Andromeda, the countless individual stars that actually belong to disrupted dwarf galaxies, now part of our galactic halo, all remind us that we live in a cosmic community, a local group of gravitationally bound partners sharing the same small volume of space in the vast, expanding universe. And as we drift toward our final reflections on this galactic journey, we carry with us an appreciation for both the intimacy and the grandeur of our cosmic neighborhood, understanding ourselves as citizens not just of the Milky Way, but of a larger galactic community that extends across millions of light years of space and billions of years of cosmic time. Close your eyes for a moment and imagine the last time you truly looked up at a star-filled sky. Perhaps you were lying on your back in a field, or sitting by a campfire, or simply stepping outside on a clear night, when something made you pause and look up. In that moment, without realizing it, you were reading the most ancient library in existence, one where every book is written in light and every story spans millions of years. The starlight touching your face in that moment carried messages that began their journey long before you were born. When you gazed up at Sirius, that brilliant winter star, you were seeing light that left its surface over 8 years ago, when you were living a slightly different version of your life. The gentle glow from Vega, once the northern pole star when the pyramids were young, has been travelling toward you since our ancestors first learned to plant seeds and tend crops. The ancient photons from the heart of our galaxy began their journey to your eyes 26,000 years ago, older than any human story we can still tell. There's something deeply moving about this temporal layering, the way each moment of stargazing becomes a kind of time travel. You're not seeing the galaxy as it exists in this instant, but as it was across vast stretches of cosmic history. Each star's light preserves a moment from the past and delivers it to your present, creating a night sky that spans millennia in a single glance. The ancient Persian poets understood something profound about this dance of light and time. They wrote of starlight as letters from eternity, cosmic messages written in languages older than human speech. To them, the night sky was a vast scroll inscribed with the stories of creation, each star a luminous word in an epic poem that began with the first breath of the universe and continues to unfold above our heads each night. When you look up at the stars, you're seeing your own family history written in light. The iron flowing through your bloodstream right now was forged in the core of a massive star that died in a spectacular explosion billions of years ago, somewhere among the spiral arms of our galaxy. The calcium that builds your bones was created in a different stellar furnace, perhaps in another part of the galaxy entirely, scattered into space by an ancient supernova and eventually gathered into the gas cloud that became our solar system. You are quite literally made of processed starlight. Your body is assembled from stellar debris. atoms that have been cycling through the cosmos for most of the universe's history. Every breath contains elements forged in stellar cores. Every heartbeat pumps blood enriched with the nuclear ashes of long-dead suns. When the medieval Sufi poets wrote about the human soul as a fragment of starlight temporarily housed in earthly clay, they spoke more truth than they could have known. There's something wonderfully circular about this cosmic recycling. The same processes that created the elements in your body are still happening throughout the galaxy tonight. Somewhere among the spiral arms, a massive star is fusing hydrogen into helium in its core, building the heavier elements that will one day become part of new stars, new planets, perhaps even new forms of life. Somewhere else, an ancient star is breathing its outer layers into space, creating those gorgeous planetary nebulae that look like cosmic flowers blooming in slow motion across thousands of years. The timescales are almost impossible to grasp. Since our galaxy settled into its current spiral shape, Earth has drifted around the galactic center about 50 times. During those long orbital journeys, countless stellar generations have lived and died, their brief nuclear fires illuminating the cosmic darkness before fading into white dwarf embers or exploding as supernovae that enrich the space between stars for future stellar families. Aboriginal Australians developed ways of thinking about deep time that feel remarkably relevant to our galactic perspective. Their dream time encompasses both mythical creation periods and the ongoing present, recognizing that the past lives within the present through patterns and relationships that span countless generations. This cyclical understanding of time mirrors the way our galaxy works, where stellar death feeds stellar birth, where the heavy elements from ancient supernovae enable rocky planets to form billions of years later. Sometimes, on perfectly clear nights, you might glimpse one of those ancient globular clusters through binoculars or a small telescope. These dense balls of old stars are like cosmic time capsules, preserving stellar populations that formed when the galaxy was young and chaotic, still growing by consuming smaller galaxies. Looking at a globular cluster is like peering into a cosmic museum, seeing stars that remember when the Milky Way was settling into its current form over 10 billion years ago. The light from these ancient stars carries more than just photons. It carries information, stories written in spectra that reveal when and where each star was born. The oldest stars shine with the chemical signatures of a simpler universe, one that contained almost no elements heavier than hydrogen and helium. Younger stars like our Sun bear the complex chemical heritage of dozens of previous stellar generations, their light revealing the gradual enrichment of our galaxy over cosmic time. Even the structure of the galaxy itself tells stories. The thick disk preserves evidence of those chaotic early epochs when things were still settling down. The thin disk, where we live, records more recent periods of organized star formation within the developing spiral arms. The vast stellar halo that surrounds our galaxy contains the scattered remnants of smaller galaxies that were captured and slowly digested during the Milky Way's growth, their disrupted stars now tracing ghostly streams and shells through space. Looking ahead, our galaxy's story is far from finished. In about 4.5 billion years, the approaching dance with Andromeda will write a dramatic new chapter, transforming our elegant spiral into something entirely different. The merger will trigger spectacular bursts of new star formation as gas clouds from both galaxies collide and compress, creating stellar populations that will carry the combined chemical heritage of both galactic communities into the far future. But even this cosmic collision will be gentle by astronomical standards. individual stars will rarely collide, separated by distances too vast for direct contact. Instead, they'll be swept into new orbits by the changing gravitational currents, their paths redirected, but their nuclear fires continuing to burn steadily. Our Sun, if it still exists, might find itself in the outer suburbs of the merged galaxy, or perhaps nearer to the bright new galactic core. The search for other life in our galaxy adds another layer to these cosmic stories. The same stellar processes that created the elements in your body have been operating throughout the Milky Way for billions of years, potentially seeding countless worlds with the raw materials for chemistry, complexity, and perhaps even consciousness. Whether or not we ever find evidence of other life among the stars, the possibility connects us to something larger than Earth, larger than our solar system. On nights when the Milky Way stretches across a truly dark sky, you might find yourself feeling a kind of cosmic homesickness, a recognition that you belong not just to this planet or this solar system, but to this vast community of stars. The galaxy isn't something separate from you, something you observe from the outside. You are the galaxy, temporarily arranged into a pattern capable of wondering about its own existence. Hindu cosmology speaks of the universe breathing in cosmic cycles that span billions of years, vast rhythms of creation and dissolution that dwarf human timescales yet somehow encompass them. Standing under a star-filled sky, you might sense something of those deep rhythms, the way our galaxy participates in processes that began with the first stars and will continue long after our sun has cooled to a white dwarf ember. The approaching merger with Andromeda reminds us that even galaxies have lifespans, that the structures we see in the night sky are temporary arrangements in an ever-changing cosmic dance. Yet there's something comforting about the slowness of it all, the way galactic evolution unfolds over periods so vast that entire civilizations could rise and fall within what amounts to a cosmic moment. Sometimes, lying under the stars, you might feel simultaneously insignificant and profound. Insignificant because human lifespans are so brief compared to stellar evolution, because our entire civilization occupies such a tiny corner of space and time. Profound because you are made of stellar material, because your consciousness represents the galaxy becoming aware of itself. Because in looking up at the stars, you are participating in a cosmic conversation that has been ongoing since the first light began to shine. The night sky connects you to every human who has ever lived, all of us passengers on the same small planet orbiting the same ordinary star in the outer suburbs of the same spiral galaxy. Yet, it also connects you to processes and scales that extend far beyond human experience, reminding you that you're part of something vast and ancient and ongoing. When you step outside tonight and let your eyes adjust to the darkness, remember that you're not just looking up at distant lights. You're seeing your cosmic family, the stellar furnaces that forge the elements in your body, the gravitational currents that shape the galaxy you call home. You're reading stories written in starlight, messages that began their journey across space and time long before you existed and will continue traveling long after you return your borrowed atoms to the cosmic cycle of creation. The stars have been waiting patiently for billions of years for someone exactly like you to look up and wonder about their light. Tonight, in the quiet moment before sleep, you can complete that ancient conversation, acknowledging the starlight that made you and carrying its stories into your dreams, where the boundaries between cosmic time and human time dissolve into the gentle rhythm of a galaxy, breathing slowly through space. And so, our gentle journey through the spiral arms of home draws to its close. We've drifted together from that first glimpse of the Milky Way stretching across a dark sky to the grand dance of galactic neighbours moving through cosmic time. We've wandered through stellar cities where different generations of stars live out their lives, traced the elegant physics that shapes spiral arms, and discovered how our small blue world has been sailing through galactic currents for billions of years. Perhaps tonight, after our travels through space and time, you'll step outside and see the night sky with different eyes. That faint river of light overhead isn't just a pretty backdrop to human affairs, but your cosmic address, your galactic home. Every star you can see with your naked eye lives in our local galactic neighborhood, fellow travelers sharing the same spiral arm, all of us passengers on the same magnificent journey around the galactic center. The darkness between the stars isn't empty, but filled with stories. Gas clouds where new stars are being born, the invisible streams of dark matter that hold everything together, the ghostly trails left by ancient galactic mergers. Even the spaces that seem vacant are part of the grand architecture. The quiet intervals between notes that give cosmic music its rhythm and meaning. Remember that you carry the galaxy within you, the calcium strengthening your bones, the iron flowing through your veins, the oxygen filling your lungs, all were forged in stellar furnaces and scattered by ancient supernovae into the space between stars. You are not separate from the Milky Way, but part of it, a temporary arrangement of stellar material that has achieved the remarkable ability to contemplate its own cosmic origins. As you drift towards sleep, let yourself feel the motion we explored tonight. You're spinning with Earth, racing through space with our solar system, orbiting the galactic center in a dance that has continued for billions of years and will continue for billions more. The motion is so smooth, so perfectly choreographed, that it feels like stillness, but you're part of an elegant ballet performed on scales too vast for human senses to perceive directly. The Milky Way's gentle spiral will continue to turn overhead, its slow arms sweeping through space while new stars are born and ancient ones fade away. Our galactic neighbours will continue their own stately orbits through the local group, with Andromeda slowly approaching for its cosmic embrace still billions of years in the future. The stories written in Starlight will keep arriving, carrying news from distant corners of our galactic home to anyone who takes the time to look up and wonder. Sweet dreams, fellow citizen of the Milky Way. Rest well in the knowledge that you belong to something vast and beautiful and ancient, that your existence is woven into the ongoing story of stellar evolution and galactic dynamics. The spiral arms of our cosmic home hold you gently as you sleep, the same gravitational embrace that has cradled every generation of stars, every planet, every possibility for wonder that our galaxy has ever contained. This is the Sleepy Astronomer, wishing you the most peaceful rest beneath the gentle spiral of our galactic home, and reminding you that you too are part of this cosmic masterpiece, forever woven into the starlit dance of the Milky Way,